So, these types of problems are very, very, very common on the AP exam. Like I would probably expect you to see several that are in this context of position, velocity, and acceleration, because they can ask you to do a lot of different things that fit in different categories for these types of problems. They could include things that might require you to do the chain rule. They can include things that, you have to understand the relationship between the velocity and the acceleration. We're going to see two particular types of questions they like to ask. Is this position moving towards the origin or away from the origin? And also, is this particle speeding up or slowing down? There's a lot of different things they can ask giving you these contexts. Sometimes you'll see them in free response questions. A lot of times if you see them in free response questions, they give you velocity as the equation that they've given you, because we don't know how to do it yet, but if we have velocity, we would take the derivative to find acceleration. And then we don't know how to do it yet, but if we have velocity and we want to find position, we would do what's called integrating, or finding the antiderivative. It's the going backwards part. We don't do that till Unit 6, but they love to give you these types of problems in these contexts because they can ask you so many different things about it. So whenever we're looking at a position graph, then what we're looking at is your x-axis on all of these is going to be some sort of time. It might be hours, it might be seconds, it might be days. There just depends on what you're talking about. I think one of the easiest things to think about here is driving, because that is a place that we use position, velocity, acceleration very often. All right. And then you would have distance here. And so, let's throw some units on this. It doesn't have to be these particular units, but driving is a context that we think of a lot for this. So let's put hours right here, and then miles right here. Kilometers if you want to be European, or really anywhere else in the world besides the U.S. But this is America. We're going to use miles, even if it is harder. We've got time here, distance here, right? Well, if we take the derivative of this function, typically, a lot of times they'll call this x of t or s of t. There's some variability on what letter they might use for that one. They'll usually tell you in the graph, in the question. They could use a different letter. It doesn't have to be X or S, but they could use any letter really for that. But that gives you a distance from whatever particular point you're talking about. A lot of times that point is the origin there, or it's a location that you're treating like the origin. And we'll see some problems like that in a second. Then if I take the derivative of this, I'm thinking of the slope of whatever function I have here, right? So if I take the derivative of this, it is going to be the slope. So the slope is change in y over change in x, which in this particular case is our distance divided by time, which if we want to put units with it, we're just using the example of miles per hour. And what is distance divided by your time? It's your velocity. You could also think of it as speed, but speed doesn't have a direction. And since our distance can be positive or negative in this case, we want to use the term velocity. Speed is always positive. So speed is like the absolute value of velocity. So like if your velocity is -5, your speed is 5. You're going backwards. Yeah, you're going backwards at 5 miles per hour. There. So velocity here your x-axis is still time in hours, but your y-axis now is velocity in miles per hour. Right? And so the derivative of your position formula is your velocity formula. Okay. Then I can take the derivative again. If I take the derivative again, this time, this would be like x double prime or v single prime, right? That is going to give us our acceleration. That's a of t. And that is because if we take our velocity graph and think of doing change in y over change in x for that, well, our y on the velocity graph is velocity in miles per hour. And then our x is still time in hours. And that velocity over time, you're changing your velocity over your change in time, is your acceleration. And your units for that are miles per hour per hour. Or miles per hour squared. So, I think position is very easy for us to think about. It is how far away you are from something, right? From whatever point you're deeming like the origin in that case. Then your velocity is easy for us to think about because we can think of it like of speed driving a car, right? It is how fast you are moving towards or away from that point, right? Acceleration, again, think of a car, right? So if you are in a car and you are accelerating, right? That means you are down there at the parking lot, you're going 0 miles an hour. You speed up just slightly to go out of the parking lot, right? So now you're going 5 miles per hour. Then you take off up Elk Spur Street and you are going 10 miles per hour, 15 miles per hour, 20 miles per hour, 25 miles per hour. Then you're not going any faster than that because that's the speed limit. And they're particularly looking for student drivers to nail on that one. And it's hard to go 25 on Elk Spur Street. That's very slow, especially if you're coming down the hill. But you're accelerating, right? Your speed is increasing, right? Depending on your driving habits, you might, accelerate faster than others, or the ability of your car to accelerate. For those of you that have living cars, in Jericho, we don't right now, but that acceleration in the positive direction, at least, is really easy for us. It's kind of easy to think about if you think about driving. We're going to talk about in a little bit what happens when you got negative directions. What happens if you have negative directions, negative accelerations? Things get a little weird then. So we'll talk about those here in a minute. But this is the general pattern. Position, take the derivative, it gives you velocity. Take the derivative, it gives you acceleration, right? And we can use this to answer questions about things. So they love to give us these super boring, very plain, but also very easy, just straightforward. A particle is moving along a straight horizontal line, or sometimes they'll say the x-axis given by this equation, right? So they give these. You've got just a particle in space. If you ever take a physics class, there are a lot of particles. They talk about a particle. They don't like talk about the car very often. They want to talk about a particle because if you simplify something down to a particle, you don't have to think about air resistance and different things that like come into play. So, so they give us a lot of these problems that are very generic. Good news about them is while they may not be seem so applicable to a real situation, they are going to be more simple because you don't have to consider as many variables. So our position is given by this equation right here. And we're only looking from 0 to 9 on time. And it wants to know what is the velocity of the particle at t equals 5. Okay, and then whether or not the particle is moving to the left or the right. So to find velocity, what do we need to do? Take the derivative. And so when you're doing something like this, here is what I would do. I think they're going to take it if you call it x prime of t or if you call it v of t. I would write it like this because you are showing the grader. You know that the derivative of x is v, is velocity. Here, and now you're free to use the letter v as velocity. If you only put 1, they're probably going to give it to you because it's very common. It's a very common notation. So I don't think they would count off if you don't put them both here. But this is like the safest, most clear, best way to write this. We're going to take the derivative, and we are just going to get negative 3 plus 2t. Okay? So you want to write this down. I know that is a super simple derivative. But write it down, and then write it down, because we need to find the velocity at 5, so you need to plug in 5. So write it down, v of 5 equals negative 3 plus 2 times 5, and we're going to get 7. Okay, so our velocity is 7. This is also an easier problem because it has no units on it, right? Like they didn't give us any units, so you don't have to worry about if this is miles per hour, feet per second, meters per day, whatever, right? Just leave the units off because I didn't put units in the problem. So we got v of 5 equals 7. There's our velocity. We need to know if the particle is moving to the left or the right. Left is your negative direction, right, is your positive direction, right? So, in this case, we would say since v of 5 is greater than 0 or is positive, that means our position is increasing. We're going further and further to the positive side. So the particle or the object is moving to the right. If you get a negative velocity, then your particle is moving in the negative direction, which if you're talking x-axis or horizontal line is going to be left. Sometimes they'll put you on the y-axis or a vertical line, and then positive is going to be up, negative will be down in that case. So sign of your velocity tells you left or right. There. Okay? Then they're going to ask us for the acceleration of the particle. So the acceleration of the particle here, if I want acceleration, I need to take the second derivative, right? So I've already established that x prime of t is v of t. So it's perfectly okay here just to do v prime of t. And I like to call it a so I remember that it's acceleration. If you want, you can also call it x double prime of t. Any of those three are fine. And the derivative of v of t is just 2, right? So a of 5 is going to be 2. So we have this question here. Is the particle speeding up or slowing down? And this is a more complicated problem than it seems like it should be. What do you guys want to, you're probably going to be right on your guess here. What do you think? Speeding up, slowing down? Speeding up. What is your reasoning? Acceleration is positive. And in this case, you are correct because our velocity is also positive. But you must consider both. Because what we have here is the thing that we're thinking of whenever we're thinking of driving a car, right? So like, imagine our object is our car, and we are driving it on a straight road. Well, at 5, our velocity was, when t is 5, velocity is 7, right? We found that, right? So if my acceleration was it is going to be the case. It's always 2, right? Because there's no other variable there. So that means at 6, what's my velocity going to be? 9. And at 7, I'll get 11. And at 8, I'll get 13, right? So my velocity is positive. That means I'm moving in the right direction. And my acceleration is positive. So my velocity is getting higher and higher and higher and higher. Okay, but we can't just say that the particle is speeding up because acceleration is positive. Because what if v of 5 equals negative 12? No, it is not. In this particular case, because the acceleration is 2, that is why on this velocity right here, it would just keep going up by 2, right? And so like your slope of that velocity is 2. Now, if we had a more complicated equation where our acceleration wasn't just 2, it was like 2t or 2t squared plus 7, then we wouldn't see that exact same thing happening. It would be a more complicated scenario. But since we're starting with a pretty simple equation, since our acceleration is constant, we're going to see that being the slope of our velocity here. Okay, so what if velocity was negative 12? Okay, let's say velocity is negative 12. All right, let's think about this scenario. This is just like a what-if scenario because it's not what's happening, right? But for us to make the assumption we're going to make on the next slide, we need to consider this. So if velocity of 5 at 5 is negative 12, so t is 5, velocity is negative 12. Well, then at t equals 6, what would the velocity be? Assume acceleration is still 2. It'd be negative 10. And then at 7, it'd be negative 8. And at 8, it would be negative 6. So when my velocity is negative 12, like if we're thinking cars, it means you're going 12 miles per hour backwards, right? Well, then you're going 10 miles per hour backwards. So if I'm thinking about speed, my speed would be at t equals 5, my speed would be 12, and 10, and then 8, and then 6. Are you slowing up, or are you speeding up, or are you slowing down? If you're talking about speed, you're slowing down. So here, acceleration is still 2, right? So a of t still equals 2. Acceleration is positive, but the velocity is negative. So your car is actually slowing down, right? So we're going to have to consider velocity and acceleration when we explain whether a particle is speeding up or slowing down. So like my reasoning right here for this, I would say since v of 5 is greater than 0 and a of 5 is greater than 0, the object is speeding up at t equals 5. So if you are asked the question about speeding up or slowing down, you have to think about velocity and acceleration. So to make some conclusions to help us with that, I have a separate slide here. If a particle is speeding up, the velocity and acceleration of that particle have the same sign. So that's what we're talking, the scenario we have here is that v of t is greater than 0 and a of t is greater than 0. The other scenario that would still be speeding up is v of t is less than 0 and a of t is less than 0. This one's hard to think of, right? This particular scenario, I think the table helps a lot. Like, let's say that we're in the same scenario. Let's say our velocity is negative, so like our velocity is negative 12, but let's say that our acceleration is negative 2 this time, right? So let's say a of 5 is negative 12. Like, this is just an example, right? So if my velocity is negative 12 and my acceleration is negative 2, now at 6 I'd have negative 14. At 7 I'd have negative 16. At 8 I'd have negative 18. So the velocity is decreasing, but if we think of what is happening to speed, I got 12, 14, 16, 18 here. So you are in some sort of action movie where you have taken off, driving backwards, speeding up, right? Like you're going down the highway backwards at increasingly fast speeds here. This is some dangerous driving, but it is still, you are speeding up. You're just speeding up in the negative direction, right? So I think that one's hard to like picture, but you can be speeding up as long as your velocity and acceleration have the same sign. So you are slowing down if your velocity and acceleration have opposite signs. And we already made a table for one of those scenarios where we had a negative velocity but a positive acceleration. If we switch that, if we have a positive velocity and a negative acceleration, we would still end up slowing down there. So this is a key to remember. They love to ask that question. Is the particle speeding up or slowing down? Or whatever they're talking about. Are they speeding up or slowing down? And it's like, even though I've taught it, a lot of kids just still answer it with acceleration. But you got to do velocity and acceleration for that. Okay. This one's a calculator active question. If you have your computer out, you can type it in, or I will put it up here too. I think that I think I might even put these in here the other day. Yeah. All right, so here is our position. So we have the position of a particle moving along a straight line at time x for 0 to 20. So here's what that looks like. This is our position. Find the times for 0 to 20 at which the particle is at rest. So, let's think about what's happening here on this graph, right? We want to know when the particle would be at rest. So this is my distance, right? This is still position right here. So like right here at this point at, oh gosh, these numbers are crazy because this is a crazy equation. Right here, I don't know why it stops right there, but at 0, 6, right? At time t equals 0, I'm 6 units away from whatever we're considering the origin to be, right? And so over here at, 1.68, now I'm only 1.93. Which way am I going here? I'm going backwards. I'm going closer to the origin, right? I'm going to the left. If it's like the x-axis, it doesn't specifically say if it's x or y. I'm going to the left, right? What about here? Still going to the left, right? Because I am here on this. In fact, let me see if I can do this. I go A, F, A. Now I want, let's do 0, F of A. Okay. No, I want the other way. I want F of A, 0. Alright, so like, watch this. This is what's happening right here. Like that particle, I can even do this. If I make this go from 0 to 20, alright, right here is what the particle is doing. Alright, so like as I go from 0, right here, that's whenever the particle's at 6, right? In fact, let me hide that. There's where the particle's at 6. The particle goes to the left, and then back to the right. Okay, that's what's happening to this particle. When does it stop? What? Almost right there at 11. It's when it turns around, right? It stops when it turns around, because if you were going to the left and you then have to turn around and go to the right, you have to stop momentarily, even if it's just for a split second, right? If the basketball coach has you running suicides and you're going down and back, you got to stop at the line and turn around to go back the other way, right? So what we're looking at is the particle is going to the left until it gets here, right? And then it turns back around and it goes to the right, okay? There's another way we can think about this. So we could definitely use, because we got this here, we could just use the minimum point of this graph, right? So we would say at x equals, let me make that, let me zoom out a little bit so I can see that. It's asking for the time, so 10.63859. Right there. So we could say at that minimum point, it's as furthest to the left as it's going to get. Then it's going back, the position is going back up, right? Or here's your another option. If you do f prime of x, it's do y equals f prime of x. It is going to graph the velocity for you. What is your velocity if you're at rest? 0, right? So if I look right here, my velocity, right here, the green graph is my velocity, and the velocity equals 0 at 10.63859, that same point, right? So we could either look at the velocity being 0, or we could look at the minimum point of that function. Also, when our velocity equals 0, that's a critical point for position, right? And our velocity changes from negative to positive, right? So we know that that's like our maximum or minimum points are going to be places where our velocity is going to equal 0. or undefined, but usually in these contexts you don't run into undefined there. All right, so our particle turns around right there where that velocity equals 0. So I've got two questions here that are very common questions that are asked. Yes?
Isn't there another point where it rests at
Possibly. Oh gosh, this is an awful question. Yes, you are right. With a big time zoom in, which probably they're not going to do to you on the AP exam. Because from the main view, does that look like it has another maximum or minimum point? It does not. But I guess really you can see it better when you look at velocity, right? Velocity, on the velocity graph, you can see it, and I should have looked at it. We do have velocity being 0 at that point. Let's count that. I don't think they'll do that to you. Like, they'll do this to you where there's two places. They just won't make it so hard to see on the graph, but evil geniuses make up the AP exam, and I might be evil to you sometimes, but I'm not a genius, so I don't make my problems quite as crafty as they do. Actually, you would be really evil if you put this on here knowing that everybody was going to miss that one because you needed to zoom out a little bit. Thanks for catching that, Molly. All right, so we actually have two places where we're at rest, right? Okay, so displacement of a particle. I always use this example. Your displacement is how far you are from where you started. So I always use this example. If you ask to go to the bathroom, and you leave my room, and you walk down to this bathroom, and they are cleaning it, and you can't go to that bathroom, and then you turn around and have to walk down here to this bathroom and go here. Your displacement from my class is the distance, let's treat the hall like it's a straight line, is the distance from my door to the bathroom, right? So your displacement is just how far you are away from where you started. Now you'll see question C says total distance traveled. Is the total distance you traveled the same as your displacement? No. If you went straight to that bathroom, then it would be. Sometimes it is the same. Displacement and total distance traveled can be the same. But displacement and total distance is not the same if you have to turn around, if you change directions, right? So for this particular case, displacement is the easier of the two to find if you have the position formula. Because all you have to do to find displacement when you have the position formula is you want to find f of 20 minus f of 0. All right. Your position at t equals 20 minus the position at t equals 0. So how far you are where you ended up from how far you wherever you were at when you started. So that's very easy to find on the calculator active problem, f of 20 minus f of 0. I've made a bad problem. Why didn't I realize this last year? It's undefined. Why is that? Because you can't do square root of 0. Gosh. All right, change 0 to 0.1. Let's change 0 to 0.1 because otherwise the problem doesn't work. Change it to 0.1. That should make it where it will work. Why is it still not working? Maybe. Let me get rid of that. No. No, I don't know why that's not working. Oh, I know why it's not. The reason it's not working here is because I was careless when I typed this in. I need an or equal to sign right there with that 20, where I restricted my domain, because it doesn't think 20 is part of the domain for that, so it's giving me undefined. But I'm pretty sure the 0 would have been a problem too, because I've got square root of 0. No, actually, it might be okay. Never mind. Okay, you can change it back to 0. I thought that was crazy that I hadn't taught that before. Because we didn't have square root of 0. We can't have square root of a negative. Let's change that back. Okay, so we've got 6.544. So this tells me that I am 6.544 units to the right side, since that's positive, of wherever I started. All right, and if you look at the graph of position there, like at 0, you're right here, at 0.6, or very close to it, and then over here at 20, you're at 12.543, so that is, or close to it, I don't know if I'm exactly there, so that makes sense, right? But your particle travels left and right. Is it the total distance? No, this particle went to the bathroom down there, was closed, had to go back to the bathroom over here, right? So, the second question is a much more difficult question. Okay? Especially with this 0.0286. So, in general, what you want to do here is you want to find position at the beginning, at the end, and at any point in between where the particle stops, where the particle is at rest. Okay? So, like I would do f of 0. Just type it in over here. F of 0 is 6. Right? That's where we start. And then we got this crazy little teeny 0.02086. So if I do f of 0.02086, then I got 6.0719. Now, from here to here, how far did I travel? 0.0719. Right, so the particle goes 0.0719 units to the right in this case. But then it turns around. At that point, it turns around and it starts going to the left. So it's going to go to the left till it gets to 10.638. So f of 10.63859. So if I find that over here, f of 10.63859 is going to be negative 11.461. Okay, so from those 2 points, I've traveled to the left. But if you're talking about total distance, it doesn't matter which direction you're going. So you can subtract those, like 6.0719 minus, make sure you do minus negative 11.461 there. And I'm getting 17.5329. And if you had subtracted them the other way, you'd get a negative, but distance is always positive. The distance you travel is always positive, so you would use the positive no matter what, right? And then the particle turns around, it goes to the right until it gets to f of 20. And f of 20 is 12.544. Okay, so from negative 11.461 to 12.544. If we subtract those two, I'm getting negative 24.005, but distance is always positive. So we'll do positive 24.005. So we basically break it down into the length of each like little leg of the trip, right? And then if we want to know total distance, we're going to add all those together. So we got 0.0719 plus 17.5329 plus 24.005. And we are going to get 41.6098. Okay, so in this case, our displacement and our total distance traveled are very different from each other, right? We're getting a lot different answers for that one. Now, if your particle only goes in one direction, your displacement and your distance traveled is going to be the same. But if it turns around at any point, they're going to be different. Okay, questions? All right, so there's a couple types of problems we've looked at. Speeding up, slowing down. We've looked at displacement versus total distance. Those are common types of problems that you'll see. Let's look at this problem. This one is one that is also total distance, but it's not a problem where they're asking us to find the exact value, right? It's a theoretical problem. So particle is traveling on the x-axis. The position is x of t. The graph gives the particle's velocity. We are looking at velocity here. Which of the following expressions gives the total distance traveled by the particle over the time from 0 to 5? Okay, so we are looking at velocity. So if I think of velocity, I'm looking at velocity from 0 to 5. Which point is of particular interest on that graph? 2. Because 2 would be a critical point of that graph, right? So my velocity between 0 and 2, my velocity is above the x-axis, so the velocity is positive. Between 2 and 5, the velocity is negative. For the position, right, what does that mean? If my velocity is positive, what does it mean about the position of the particle? Okay, that position is increasing, or you can also think of it, since we're talking about x-axis, you can think of it as going to the right there, okay? And between 2 and 5, if my velocity is negative, that tells me that position is decreasing, which means that that position is going to the left. So, this particle changes directions, right? So since the particle changes directions, and they're asking me for total distance, I can't just do displacement, right? If this velocity was just above the x-axis the whole time, or below the x-axis the whole time, I could just do displacement, and that would give me the correct answer. But I can't do that. Now, if you look at answer choice A, this is the displacement. The displacement is when we just take position at the end minus position at the beginning. And displacement is not what they're asking us for here, so it's not A. Would it make sense to subtract velocity at 5 minus velocity at 0? That gives you like the change in your velocity, but does that have anything to do with how far you went? I mean, not really, so D's not a reasonable answer either. Okay, here's what we've got to consider. B and C are very similar answers. We have to consider the like x of 0, x of 2, and x of 5. right? So, x of 0 is our starting point. Doesn't really matter where that is at, right? Let's give it, I like to throw some numbers in here so it's a little more concrete to deal with. Let's give x of 0 a number. Marley, what number you want to use? Doesn't matter. You can pick anything. 8. So if we pick 8, this could literally be any number. Does not matter, right? So if x of 0 is 8, then it does matter what number we pick for 2. Because what is the particle supposed to be doing from 0 to 2? It's supposed to be going to the right, or increasing. So, Connor, give me a number for 2. There's a lot of options, although there are some wrong options on this one.
So x of 2 needs to be greater than x of 0, right?
Correct.
So, okay,
10. So 10 would be beautiful. Anything bigger than 8 works, right? Okay? And then we've got to think of what's happening for x of 5, right? Now our particle on this interval from 2 to 5 is supposed to be going to the left. So, Kendall, what do you think? What could we use for x of 5? 6 would be beautiful. Anything less than 10 works here. Now, I probably also would have gone lower than 8 like you did, but you don't have to. It could be 9 right there would be fine. We just have to have a lower number. So, distance is always positive. So, if I'm finding this amount right here, from 8 to 10, how far did I go? 2, right? It's an easy question to answer. So, am I doing x of 0 minus x of 2, or am I doing x of 2 minus x of 0 to get 2? X of 2 minus x of 0. Because if I do x of 0 minus x of 2, I will get a negative number, right? That'll be 10. That'll be 8 minus 10, which will give me a negative number. So that's this part. We actually don't have to worry about that too much because both of our answer choices look like that here on that first part. Then, if I want to know from 10 to 6, if I go from 10 back to 6, I traveled 4 units, right? How do I get that? X of 2 minus x of 5, or x of 5 minus x of 2? To get a positive number, I got to do 10 minus 6, right? Which means I've got to do x of 2 minus x of 5. So, C is going to be the correct answer there. And now take those two and add them together. I traveled 2 here, 4 here, 6 altogether. So you really just need to think about, like, which value would be greater right there. I think the easiest way to do that is throw some easy numbers on it and then think about what's happening with those numbers. Okay. All right. Okay, we're going to do 4. We're going to skip 5. And then we're going to try to do, we're going to do 6, but we're probably going to have to turn 6 into a calculator active question. It's not supposed to be. Skipping 5 is going to make one of your homework questions possibly undoable, but we might look at it tomorrow. All right, so this is calculator active. I think I already have this over here on Desmos too. Let me get rid of a lot of this stuff that we were doing. Okay, so we've got v of t is our velocity, and our question says, at what time is the particle furthest to the right? So, if we were looking for furthest to the right and we had position, we could just, if we were looking furthest to the right and we had position, we could just see where our position was highest, right? That would just be our answer. But they only gave us velocity. So, we are looking at this velocity here, and it appears that velocity is positive here, and then right here at 110.56854, we switch our velocity to negative. Does it look like it changes anywhere else? Don't think so, right? That's it. That's our only critical point of our velocity, right? So what that's telling me is velocity, we're starting at 0 at, let's see, what was that number? 110.568. That's 569 if we round it. Velocity is positive on that first interval. Velocity is negative on the rest all the way to infinity. So what does velocity tell me about position? Right? So if velocity is positive, position is increasing. Which direction is that going to be? Right. And then whenever my velocity is negative, my position is decreasing, which is to the left. So if the particle goes to the right for a while, then it turns around and goes to the left forever, when's it furthest to the right? At the turnaround spot, right? That's as far as it went. So it's only asking for the time, not the actual position, because we don't have position formula here. So at time equals 110.569, we see that's our turnaround point, and it's our only critical point that happens. So you got a couple ways that you could explain this. You could say that the particle is furthest to the right at t equals 110.569 because v of t changes from positive to negative, which indicates the particle changes from traveling right to traveling left. Okay, and this is important. So we've got this switch in velocity from positive to negative. We also must say, and t equals 110.659 is the only critical point of v of t. Because a velocity switching from positive to negative only tells us a relative maximum or minimum, right? Unless it's the only critical point, and then it has to be absolute. So, so that last line here is really important. Okay, we're gonna skip the next one. We're going to turn 6 into a calculator active question. It is not supposed to be, but we're going to make it one, because if we don't, it makes it difficult. So I changed t's to x's when I typed this in, because while you can get it to graph y of t, if you try to do y prime of t, it doesn't like to do that. So I am going to just change it to x's here, and then t is greater than 1/2. Oh, I got to put squiggly brackets. So x is greater than 1/2. So we know which part of the function that we're looking at right here. Writing the equation for velocity is going to be something that you would have to do the actual process for there. So we're kind of skipping A as well because we're doing this in the calculator. I'm going to do, I wonder if it'll do this, y equals y prime of x. Okay, it does not like the fact that I have, y of t is problematic for Desmos because Desmos thinks y is the y-axis, right? It doesn't have to be. You can represent it this way, but Desmos is having a fit with this y right here, so let's just make it f of x, right? So then if I do y equals f prime of x, it won't graph the derivative for me. Why? Oh, that's it. You're right. I'm trying to save myself time. I'm making things more complicated for myself. Okay, I got two f of x's. Now it knows what I'm talking about, right? So then it will give me the graph of velocity. So rather than actually finding it by hand like we were going to do if we had enough time, we're just going to look at the graph, right? Okay, so at time t equals 3 over pi, is the particle moving toward or away from the origin? Now, this is a little bit like the speeding up or slowing down problems. We've got two things we've got to consider. Now, we definitely need to know whether this particle is going to the left or to the right. With this being calculator active, that's very easy to find. F prime of 3 over pi. Right here. Right, that's all I got to do. F prime of 3 over pi is negative. Now, this can be done without a calculator, but we are just out of time. Try to do the one on your homework like this without a calculator if possible, but if you're desperate. Okay, so that is less than 0. What does that tell you about the particle? Particle's moving to the left. So is the particle going towards or away from the origin? The answer depends on where the particle is at, right? Because if the particle is here and moving to the left, then it's going to be going towards the origin. But if the particle is here and moving towards the left, then it's going away from the origin. So a lot like speed, to speeding up or slowing down problems, you can't just consider acceleration. So here we can't just consider the direction the particle is going. We also have to know the position of the particle. So position of the particle just means that we need to plug in 3 over pi into the original function. And so f of 3 over pi, which again can be done without the calculator, but we just don't have time, is going to be 0.716 right there, which is greater than 0. So the scenario that we're looking at here is this one right here, the one I've got in red, because our position is positive, which means we're starting off to the right of the origin, and our velocity is negative, which means that we're moving towards the left. So we're looking at this scenario right here, where our particle is moving towards the origin. So to summarize here, if this is for your response question, you got to give reasoning. So I would say since f of 3 over pi is greater than 0 and f prime of 3 over pi is less than 0, the particle is moving towards the origin. So, summarizing really quickly. Oh, good gracious. We got to fill in this last thing right here. If the particle is moving towards the origin, position is positive, let's just do signs. That'll be quicker. We can get it done. Positive and velocity is positive, or position is negative and velocity is negative. No. Gosh. Switch these last two. All right, so if you have opposite signs for position and velocity, then the particle is moving towards the origin. If the particle is moving away from the origin, you've either got positive, positive, or negative, negative in that case. All right, so got a worksheet. Let me pass that out to you. Which number is it? It's going to be bad. Which one looks like that number that we skipped? Is it? 3. Number 3 you can skip on here. The rest of them, you should at least be able to get like an idea of it. If you're desperate, use the calculator, even if it's not calculator active. But hopefully you can do something.